Yes, so we're happy to be here to present FRIGG. This is Renal. My name is Lene Nysen. And FRIGG is an acronym for Fresh Human Kidney Tissue, Exploring Biomarkers and Intervention Targets in Chronic Kidney Disease.
Chronic kidney disease affects about 10% of the general population worldwide, corresponding to over 800 million individuals. The global mortality rate has been increasing with over 40% from 1990 to 2017. And if you take a look at the rank in cause of death, it actually been predicted to suggest that chronic kidney disease will become the 5th highest cause of death globally by 2040. The hallmark of chronic kidney disease is renal fibrosis. And if you go from a healthy state to a state with more persistent injury due to different disease states, as for example, diabetes, high blood pressure, obesity, just to mention a few, you would over time develop kidney fibrosis, which is then leading into chronic kidney disease. In severe cases of chronic kidney disease, you develop end-stage renal disease and then in a need for kidney transplantation in order to get into a more healthy state again. This slide here is showing different targets which has been successfully able to reduce renal fibrosis in different preclinical animal models. However, when it comes to a more clinical setting, almost none of these drugs is used in the clinic. So there is really a need for finding better targets which can help reducing renal fibrosis in patients with chronic kidney disease.
So this is the FRIGG team. So we are groups, Renal and my group at Department of Clinical Medicine, as Lindland's group at Biomedicine, and also Mia Madsen and Anna Keller from Aarhus University Hospital, Department of Urology, as well as Jørgen Klems from iNano. And then there are several students and staff involved. From industry, we have AstraZeneca, Novo Nordisk, and Nordic Bioscience. And the aim of FRIGG is to model early stages of human chronic kidney disease development to identify both novel chronic kidney disease biomarkers as well as targets, and also to evaluate the translatability between human and mouse chronic kidney disease models for target validation.
So here we show the experimental setup. So we use fresh human kidney tissue, which we get from patients which has their kidney removed due to renal carcinoma or due to fibrotic conditions with chronic kidney disease. We get the healthy part of the kidney, which is as far away from the tumor as possible. And we get a part down here from the fibrotic tissue. We then make biopsy punctures, and using a chrome disc slicer, we are able to make small slices, which has a diameter of 5 millimeters and a thickness of 200 to 300 micrometers. We are then able to culture these slices up to 48 hours and treat them with different conditions. We then take the slices and we use them for different analysis, for example, qPCR, Western blotting. We do viability imaging, and we also doing spatial transcriptomics. And we also take the medium for measuring different biomarkers. This is the patients we have included so far. The inclusion is done by Mia and Anna from Department of Urology. And I just want to highlight on this slide here that we have a lower GFR in the patients where we get the fibrotic tissue compared from the healthy. Here we show that we are able to force these human kidney slices into an inflammatory and fibrotic profile. This is done by Camilla and Gitte. And what they do is that they culture these slices up to 48 hours and they treat them with different compounds, TNF-alpha and GDF-beta. If you take a look at the upper panel here, you can see that after treatment with TNF-alpha, we are able to increase inflammatory genes like TNF-alpha and interleukin-1 beta. And you see that we have a high variability between our patients as we actually expected, but they are all increased after treatment. Taking a look at the lower panel with the fibrotic profile, we are able to increase different fibrotic genes like collagen and fibronectin after 48 hours of treatment with TGF-beta.
So Andreas Rieshede is an MD, and he is doing histopathology on the sections to evaluate the progress of fibrosis and inflammation. And here first he compared samples from a normal kidney at baseline 0 hours with a sample from a chronic kidney disease patient also at baseline for 0 hours. And what you see in the sample from the chronic kidney disease patient is that you have glomerulosclerosis, there is interstitial fibrosis, tubular atrophy, and also inflammation. Andreas then went on to look at mesenteric stains, and here we look at baseline 0 hours of a control and also 48 hours untreated. You can see a marked difference in what the tissue looks like at 48 hours untreated compared to 0 hours. So we see shrinkage of the tissue as expected, and we also see deposition of extracellular matrix, where you look at the blue color here and you can see a larger area of extracellular matrix. So by culturing the slices for 48 hours, we have induction of fibrosis. But when we then compare them to 48 hours of TGF-beta treatment, we can see that TGF-beta has a marked effect. We have a much larger area of extracellular matrix deposition, as indicated here by the blue color. So Camilla also looked at the mRNA levels. So she first looked at baseline of a control slices compared to fibrotic slices. And what she saw was that fibronectin, collagen, and alpha SMA, all markers of fibrosis, are higher in the fibrotic samples compared to the control. When she then compared to 48 hours of culture with control, TGF-beta, and the fibrotic, we can see that fibronectin, collagen, and alpha SMA are induced in the TGF-beta, but actually the expression levels are higher in the fibrotic tissue as expected.
We are also in the process of performing spatial transcriptomics, and this is done by Lin from Department of Biomedicine together with Camilla. And just to give you a very brief overview of spatial transcriptomics. The spatial transcriptomic platforms utilize slices containing 4 capture areas, each with 5,000 molecular barcodes, spatially encoded spots, over which an intact frozen tissue section is placed. It's then stained, imaged, and permeabilized. The permeabilization results in a release of the mRNAs, transcripts from the tissue that are then directly captured by 200 million oligonucleotide capture probes. These unique spatial barcodes then allows the transcripts to be mapped directly to their exact location on the tissue section. Lin is then performing imaging, and RNA sequencing data are then processed together, which can then be sold in a whole transcript gene expression map directly into the tissue image. And what Lin has done here is she is in the process of confirming the method. Here she looked into the glomeruli, which is very much existing of podocytes. And here we also see an increased expression of podocin. Lin has also done evaluation, again looking at collagen 1 and at a macrophage marker. And what we actually see here is that we see a higher expression of collagen 1 in slices with TGF-beta treatment compared to the non-treated, as well as the slices treated with TNF-alpha. If you look at the lower panel down here, we see a higher expression of the macrophage marker after TNF-alpha expression, after TNF-alpha treatment compared to TGF-beta treated and untreated. She is also in the process of looking into hallmark pathway analysis, which is a tool where you can look into specific activity of pathways. And what she actually did here is looking into an inflammatory as well as TNF-alpha signaling pathway via NF-κB. And as expected, we do see an increase of activity of these pathway in the slices treated with TNF-alpha compared to the GDF-beta and untreated slices.
So the next step is to now validate all these targets that Lyndon has found in the spatial transcriptomics and to obtain a higher resolution. And to do that, Gitte and Søren are working with immunohistofluorescence of the targets. And to optimize the use of tissue and for speed, they developed a new multiplex protocol for immunohistofluorescence. So the first step was to, instead of using the regular objective glasses, they use very thin cover slips, which they clean thoroughly, and then they can adhere the paraffin section with the tissue onto the cover slip. They can then deparaffinize, do target retrieval, and block for unspecific binding, and then do a standard immunofluorescent labeling on the cover slip, followed by imaging. And the imaging is done in a very simple chamber with PBS, so there's no mounting with mounting media. After the imaging, where they do large stitches to obtain the whole biopsy sample, we can do antibody stripping and restaining and then imaging. And we can do this for multiple rounds. And afterwards, they use alignment software to align all the images to do an overlay. So one positive aspect of this is that we get increased resolution. If you look here, this is a glomerulus stain on a regular Superfrost Plus slide, and this is on a glass cover slip. And what you can recognize is that we have increased resolution actually corresponding to the resolution of a confocal microscope, although these images are actually acquired on a wide field epifluorescent microscope. So this is one huge advantage of placing your tissue on a cover slip. And then they're of course able to do the multiplex staining. So this is a kidney section, this is from mouse. And then they have stained for different markers of the cortex, outer stripe of outer medulla, interstripe outer medulla, and inner medulla, specifically for proximal tubules, collecting ducts, glomeruli, vasculature, and loop of Henle, and can then do the overlay to see how these proteins are expressed and localized in respect to each other. And when they terminate the staining, they terminate it with an HG stain, so we can compare with morphology. So here you can see this is collecting duct, which you can also see in the HG stain here. What is also obvious that this is a little bit harsh on the tissue, so you have breakage, especially you can see it here in the inner medulla, but it's very efficient to do multiplex staining.
And we are also looking into different biomarkers. This is done in collaboration with Nordic Bioscience, which is a company very much specialized in measuring extracellular matrix biomarkers. So Alexandra has measured biomarkers in the medium from our slices, looking at a lot of different extracellular biomarkers. And here we show an example of collagen 1 and again fibronectin. And she shows very nice increased secretion of these biomarkers into the medium from the slices over time. She also performed correlation analysis back to the gene levels, and she showed a very nice correlation between the mRNA and the protein level for both collagen 1 as well as for fibronectin.
So that is the status of the FRIGG project. So then we were also asked to tell a little bit about the pros and cons of working in an open collaboration. And some of the pros are definitely the ideation process with the multiple industrial partners, because they were able to contribute to the project ideas and had very different views on it. And they were also able to share their needs. What would they really like us to do in this project? We also have multifaceted competences and methods between the companies where they are able to do some analysis that we cannot do here in our groups. We're able to share samples, so we're planning to send some of the sections to Novo Nordisk and AstraZeneca, and also the media is shipped to Nordic Bioscience. We have rapid sharing of data. What has been difficult in the process is to obtain the MTAs to share the samples with the companies, and this is the human samples. FRIGG has been in charge of that, and that has been a very lengthy process, which she has just terminated now. It's taken 1 year to get these MTAs approved. And then for closed projects, of course, we are hoping that this platform that we are now characterizing can be used in closed projects for target validation with the industrial partners. So that is all from us. So we're happy to take any questions.